Hello everyone, I am Himanshu Vasnani from engineering. Subject non-destructive evolution and testing. Subject code Amico 19, unit number 4, and lecture number 22 in the series. And today's topic are magnetic particle testing, working principle, and concept of magnetism. So let's start the lecture for today. So our learner objective for today is to provide the students with a basic understanding of magnetic particle testing, that is the working principle of MPT, sorry, and to know the concept of magnetism. And our outcome after the lecture will be the students will have an understanding of MPT, that is magnetic particle testing of the principle, and the students will understand concept of magnetism. So let's start with it. Before let's starting with MPT, I want to tell you that we have been discussing the non-destructive evaluation techniques like visual inspection, like liquid penetrant testing inspection, and radiographic inspection, and ultrasonic testing. So after this, we are going with the magnetic particle inspection. Uh, the as the name says, magnetic particles. So normally, the you can say the major requirement is that it should be used with some kind of materials that can be magnetized. Okay, so let's start with it. So magnetic particle testing is one of the most widely utilized NET methods since it is fast and relatively easy to apply, and part surface separation is not as critical as it is for some other methods. Okay, so they say that it is relatively faster and relatively easy to apply. Why? Why? Because the part surface preparation is not critical there as we compare it with the other methods that we have discussed before. So this method uses magnetic fields and small magnetic particles like as iron fillings to detect flaws in the components. Okay, the only requirement from an inspectability standpoint is that the component is being inspected must be made of a ferromagnetic material, that is the material that can be magnetized, such as nickel, iron, cobalt, and some of the alloy. The basic condition and you can say the thumb rule is that the component that you want to inspect or the want to test should be made of ferromagnetic material. That means the material that the material can be magnetized. And we have given examples like as iron, cobalt, nickel, and some of the alloys. Okay, so here what the in MPT what happens that this it uses magnetic fields and small magnetic particles, for example, iron fillings, to detect the flaws in the components, and the components should be made of ferromagnetic materials. Uh, so this method is used to inspect a variety of products from castings to forgings and weldments. So far, we have been discussing about the various defects that can be found in the weldments. Okay, and various welding inspections have been done through radiographic testing and ultrasonic testing. Okay, and regarding casting also, we have been working on the various defects that can be caused in the castings, like in radiographic testing also. So this MPT, that is the magnetic particle testing, can also help you to inspect a variety of defects in maybe in the casting or forging and weldments. Okay, so many different industries use magnetic particle inspection, such as structural steel, and automotives, and petrochemical, power generation, and aerospace industries. So these industries have been using this kind of MPI, magnetic particle inspection technique, for their different processes and for detecting the any flaw or defect in these. Underwater inspection is another area where magnetic particle inspection may be used to test items such as offshore structures and underwater pipelines. Obviously, underwater pipelines should be tested regularly in order to avoid some leakage. Okay, so for this, they normally go for MPI, magnetic particle inspection. Okay, now the basic principle of this MPI, magnetic particle inspection, or MPT, magnetic particle testing. Okay, in theory, the magnetic particle testing has a relatively simple concept. Okay, so it can be considered as a combination of two non-destructive testing methods. That is, the first one is magnetic flux leakage testing, and then visual testing. Okay, visual testing we have also discussed in liquid penetrant testing, with the name of visual inspection. okay, for testing the surface of the workpiece for any defects or flaws. So here they are saying that the MPT, magnetic particle testing, concept can be considered as a combination. Okay, this MPT testing, magnetic particle testing concept can be considered as a combination of two non-destructive testing methods. One is the magnetic flux leakage testing, and second is the visual testing. So for the case of a bar magnet, you can see in the right hand side, the bar magnet, the magnetic field is in and around the magnet. Okay, you can see the lines, magnetic lines going. Okay, from the in the right hand side, you have the north pole on the left and you have the south pole on the right. In the diagram on the right hand side, you have a bar magnet with it. So the magnetic field is in and around the magnet. So any place that a magnetic line of force exits or enters the magnet is called a pole. So normally the magnetic lines of force exits a magnet from north pole and enters from the south pole. So this is a kind of a rule that say that the for the bar magnet the magnetic field is around the magnet. Okay, so any place that a magnetic line of force exits or enters the magnet, okay, is called a pole. And normally they say that the magnetic lines of force they exit from the north pole and they enter from the south pole. So in this way you can easily identify the magnetic field or magnetic lines of force. Okay, now when a bar magnet is broken, you can see the diagram on the right hand side, a kind of a bar magnet that has been somehow broken in between. Okay, so when a bar magnet is broken in the center of its length, uh, two complete bar magnets with magnetic poles on each end of each piece will result. Okay, they say that if you break the bar magnet from the center of its length, so what happens that you will get a two complete bar magnets with magnetic poles on each end. Okay, you will get two complete bar magnets with some magnetic poles on each end of each piece with result. You will get this. So if the magnet is just cracked but not broken completely in two, now the first one condition was saying that if it is broken, then you will get two complete bar magnets. Okay, and they will have their own magnetic poles on each end of each piece. Okay, now the same condition is that if the magnet is just cracked, not broken completely in two, so a north and south pole will form at each edge of the crack. Okay. Now the poles, that is north pole and south pole, these are formed at the edges of the crack. Okay. Now the magnetic field the exits the north pole and re-enters at the south pole. Okay. Now here what happens that the magnetic fields they are exiting the north pole. You can see in the diagram, and then they are re-entering at the south pole. So the magnetic field spread out when it encounters the small air gap created by the crack because the air cannot support as much magnetic field per unit volume as the magnet can. Okay, so when the field spreads out, it appears to leak out of the material and this is called as a flux leakage field. Okay, now you can see the flux leakage shown in the diagram on the right hand side. So they say that if the magnet is just cracked, okay, you can see the crack, but not broken. Okay, so when it is not broken, then a north and a south pole is formed at the edges of the crack. Okay, and at the edges, the magnetic field exits the south pole and re-enters at the the magnetic field exits the north pole, exits the north pole and re-enters the south pole. So here what happens, the magnetic field spread out when it encounters a small air gap created by the crack because the air cannot support as much magnetic field per unit volume as the magnet can. So when the field spreads out, okay, it appears to leak out of the material and this is called as a flux leakage field. Okay, so just remember thing that the magnetic field exits at the north pole and re-enters at the south pole. So if iron particles are sprinkled, okay, now the thing comes. If iron particles are sprinkled on a cracked magnet, okay, the particles will be attracted to. Okay, now what happens? You are sprinkling iron particles at the cracked magnet. So the particles will be attracted to and cluster not only at the poles, at the ends of the magnet, but also at the poles, at the edges of the crack. Okay, now the iron particles, if you sprinkle iron particles on a cracked magnet, what happens that the particles will be attracted to and cluster not only on the poles that we are having of the bar magnet at the ends of the magnet, but also at the poles, at the edges of the crack. Okay, at the edges of the crack. Okay, the cracked edges you can see in the diagram where the flux leakage is shown. So the iron particles will also be attracted at the poles of the edges of the crack also. Now this cluster of particles is much easier to see than the actual crack. Okay, you can easily locate this cluster easily. Okay, this cluster of you can say iron particles at the crack. Okay, you can easily see them than the actual crack, and this is the basis for magnetic particle inspection. Okay, now this is helping you to easily found the crack by just sprinkling the iron particles, and then the iron particles they form a cluster of air at the edges of the crack, and in this way you can easily find out the actual crack because it is much easier to locate the cluster than the actual crack. So if you see the cluster of you can say iron particles there, then you can easily find out the actual crack. Okay. So the first step in a magnetic particle testing is to magnetize the component that is to be inspected. Okay. Now we are going for the testing procedure. So the first step in the magnetic particle testing is to magnetize the component that is to be inspected. So if any defects on or near the surface are present, the defects will create a leakage field. Okay. If any defects on or near the surface are present, the defects will create a leakage field. Okay. You can see also that I have showed you the leakage field was there. Okay. Now after the component has been magnetized, iron particles either in a wet or dry or wet suspended form are applied onto the surface of the magnetized part. Okay, I repeat what happens that if the after the component has been magnetized, so iron particles either in a dry or wet suspended form are applied to the surface of the magnetized part. Okay, then the particles will be attracted and cluster at the flux liquid field and cluster at the flux leakage field, thus forming a visible indication that the spectre can inspect. Okay, now it is for the inspector. You can see in the diagram on the right hand side. Okay, you can see the green portion. Okay, this is what is magnetic particles. Okay, and there you have a crack, and you can see from the north to the south pole how the magnetic lines are flowing. That it is leaving from the north side, and it is re-entering at the south side in the south pole. So here what happens that the magnetic field lines are flowing. So what they do to find what the inspector does, they first what to do that they try to first magnetize the component that you want to inspect. Okay. Then after that, if there is any defect or a leakage, then you know, or if a defect or leakage or a crack is there, then you know that it will create a leakage field when you go for the magnetized when you have when the component is magnetized. Then after that, know that the if the component is magnetized, then you can use iron particles that may be in the form of dry or wet suspended form, and you can apply this on the surface of the magnetized part. Now these iron particles will be attracted and they will cluster at the flux leakage fields. Okay, and in this way they form a clear visible indication for the inspector that there is a crack or a defect at that point in the workpiece. And that then that defect can be then after that easily found by the inspector also. Okay. Now the advantage and disadvantages of this work, that the primary advantage and disadvantage is like when compared to other methods are like the advantage like high sensitivity, that is the small discontinuities can be detected. Then indications are produced directly on the surface of the part and constitute a visible representation of the flaw. Okay, the sensitivity is really high. Okay, and obviously then the small discontinuities, these can be found out. And moreover, the indications are whatever you are trying to indicate with the help of iron particles, they are produced on the surface of the part, you know. And obviously, if anything is on the surface, then it will be a good visual representation of the flaw. Okay, then again, you don't need to have any paint, so the minimum surface preparation is there for this. Okay, here for this, there you have the since there is no need for paint removal, so you can see that the minimum surface preparation is to be done. Then it is portable because you can say the small portable equipment and materials available in spray cans, and the important thing is it is inexpensive, like it is having a low cost, and the materials and the associated equipment are relatively inexpensive for that. Okay, disadvantages for that also, that only surface and near surface checks can be detected, obviously because the surface and the near surface areas can be detected for that. Only applicable to ferromagnetic materials that we have just discussed in the starting only. Then relatively small area can be inspected at a time. Okay, relatively small area can be inspected at a time. Okay, then only materials with a relatively non-porous surface, only materials with a relatively non-porous surface can be inspected. Okay, then the inspector must have direct access to the surface being inspected. The inspector must have direct access to the surface being inspected. So that was a slight glimpse of the MPI, that is the material particle inspection, or MPT, magnetic particle inspection, or a magnetic particle testing. Okay. Now let's go with the technical term known as magnetism. Okay. So the concept of magnetism centers around the magnetic field and what is known as the dipole. Okay. The term magnetic field simply describes a volume of space where there is a change in energy within that volume. Okay. This is saying that the magnetic field simply describes a volume of space where there is a change in energy within that volume. So the location where the magnetic field exits or enters a material is called a magnetic pole. We discussed this previously also, that the pole is the location where the magnetic field enters or exits a material. It's called a magnetic pole. So magnetic poles have never been detected in isolation, but they always occur in pair. Obviously, North Pole and South Pole, so they always occur in pair. So hence the name is called as dipole. Okay, hence the name is called as a dipole. So that is why in the starting we said that the concept of magnetism centers around the magnetic field. Okay, the concept of magnetism centers around the magnetic field and what is known as dipole. And then the dipole is explained like this. Then therefore a dipole is an object that has magnetic pole on one and a second equal but opposite magnetic pole on the other. Okay, it is saying that a dipole is an object that has a magnetic pole on one end and a second equal but opposite magnetic pole on the other. So a bar magnet is a dipole with a north pole at one end and south pole at the other. A bar magnet is a dipole with a north pole at one end and south pole at the other. Now the source of magnetism, this lies in the basic building block of all matter, the atom. Okay. Now, atoms are composed of protons, neutrons, and electrons that we know. So, the protons and neutrons are located in the atom's nucleus, and the electrons are in constant motion around the nucleus. So, the electrons they carry a negative electrical charge. Okay, the electrons are constant motion around the nucleus, and they carry a negative electrical charge and produce a magnetic field as they move through the space. Okay, these electrons they produce a magnetic field as they move through the space. So magnetic field is produced whenever an electrical charge is in motion. Okay, whenever electric charge is in motion, a magnetic field is produced. And the strength of this field is called as magnetic moment. Okay, we say that a magnetic field is produced whenever an electrical charge is in motion, and the strength of this field is called as the magnetic moment. So when the electric current it flows through a conductor, when an electric current is flows through a conductor, the movement of electrons through the conductor causes a magnetic field to form a conductor. Okay, when an electric current flows through a conductor, this movement of electrons, okay, through the conductor causes the magnetic field to form around the conductor. So the magnetic field can be detected using a compass. Since all matter is comprised of atoms, so all materials are affected in the same way by a magnetic field. However, the materials do not react the same way to a magnetic field. So the reaction of materials to magnetic field. Now we're going for the reaction of materials. Okay. So let's now go with it. When a material is placed within a magnetic field, the magnetic forces of the material's electrons will be affected. Okay. Whenever a material is placed within a magnetic field, then obviously the magnetic forces of the material's electrons will be affected. So this effect is known as Faraday's law of magnetic induction. Okay, you know the importance of electrons we just studied in the last slides. Now they say that whenever you place a material it within a magnetic field, then obviously the magnetic force of the material's electrons, okay, they will get affected. And this effect is known as Faraday's law of magnetic induction. Now, however, materials can quite react quietly different to the presence of external magnetic field, and the magnetic movements associated with atoms have three origins. Okay, like the electron motion, the change in motion caused by an external magnetic field, and the spin of the electrons. Okay, the magnetic movements that was there associated with the atoms have three origins. The first one is the electron's motion. Then the second one is the change in motion caused by an external magnetic field, and last the spin of the electrons. Okay, so in most atoms, the electrons they occur in pairs, where these pairs spin in opposite directions. Okay, what happens? The electrons they occur in pairs and they spin these pairs in opposite directions. So the opposite spin direction of electron pairs cause their magnetic field to cancel each other. The opposite spin directions of electrons pair causes their magnetic field to cancel each other. Cancel each other. So therefore, no net magnetic field exists. Alternatively, magnet materials with some unpaired electrons. Alternatively, materials with some unpaired electrons will have a net magnetic field and will react more to an external field. Okay, if you have some unpaired electrons, you will have a net magnetic field because these that are not cancelled. That are not cancelled. Okay, and then they will react more to an external field. So according to the interaction with the magnetic field, the materials can be classified as you can classify them into like diamagnetic materials. Okay. Now these materials are those which have a weak negative susceptibility to magnetic fields. Okay. Now diamagnetic materials are slightly repelled by a magnetic field, and the materials does not retain the magnetic properties when the material and the external field is removed. Okay. Now they are weak. Okay. Diamagnetic materials are weak, and they to the magnetic fields. Okay. And the materials, okay, they do not does not regain the magnetic properties when the external field is removed. So in diamagnetic materials, all the electrons are paired, so there is no permanent net magnetic moment per atom. Okay, since the electrons are paired, there is no free electron, all are paired, so there is no permanent movement net magnetic moment per atom. So most elements in the periodic table, including copper, the silver, and gold, are diamagnetic. Those materials like copper, silver, and gold are diamagnetic. Okay, they are examples of diamagnetic materials. Okay, so now the paramagnetic materials. Now these are have a small positive susceptibility to magnetic field. Okay, now, these materials are slightly attracted by a magnetic field, and the material does not retain the magnetic properties when the external field is removed. Okay. Now, the previous diamagnetic materials are also slightly repelled by the magnetic field, but here, in case of paramagnetic materials, these materials are slightly attracted by a magnetic field, and here the material does not retain the magnetic properties when the external magnetic field is removed. Now, there is an improvement in case of you can say attraction. So paramagnetic materials have some unpaired electrons. Now this is due to that these paramagnetic materials, they have some unpaired electrons in it. So examples of the paramagnetic materials include magnesium, molybdenum, and lithium. Okay, some examples of paramagnetic materials are like these are paramagnetic materials like include magnesium, molybdenum, and lithium. So now comes the ferromagnetic material. Okay, and as the name says, ferromagnetic materials, that we also know that they have a strong attraction, okay, to magnetic fields. So let's discuss on this. Ferromagnetic materials have a large positive susceptibility to external magnetic field, and they exhibit a strong attraction to magnetic fields and are able to retain their magnetic properties after the external field has been removed. Now, this is what the properties of ferromagnetic material you can say have an advantage over the other paramagnetic or diamagnetic materials. Okay, now they are you can say are they have a strong attraction to the magnetic field, and the most important thing that they are able to retain their magnetic properties after the magnetic field has been removed. Now, ferromagnetic materials have some unpaired electrons, so their atoms have a net magnetic moment. They get their strong magnetic properties due to the presence of magnetic domains. Now, in these domains, you can say that the large number of atoms movements are aligned parallel so that the magnetic force within the domain is strong. Okay. Now this happens during the solidification of the material where the atom movements are aligned within each crystal, that is grain, causing a strong magnetic force in one direction. Okay. Now these ferromagnetic materials, they have a kind of unpaired electrons with them. Okay, and due to that the atoms, they have a net magnetic moment, and so that they get their strong magnetic properties for that. Now, when a ferromagnetic material is in unmagnetized state, the domains are nearly randomly organized. Okay, you can see in the diagram on the right hand side an unmagnetized material. You can see that how the domains are randomly organized. Okay, and since the crystals are in arbitrary direction, and the net magnetic field for the part as a whole is zero. So when a magnetized force is applied, okay, the domains become aligned to produce a strong magnetic field within the part. You can see that how the domains are getting aligned and a strong magnetic field is produced within the part. Examples are like iron, nickel, and cobalt are examples of ferromagnetic materials. Okay, and components made of these materials are commonly inspected using MPM, magnetic particle method or magnetic particle testing. So this is a kind of small, you can say, explanation of ferromagnetic materials and their importance. Okay, you can see in the diagram how the unmagnetized materials, okay, the domains look like how randomly organized. But whenever you magnetize the materials, you see that the how these domains are aligned and they produce a strong magnetic field within the part. Okay, and the iron, nickel, and copper. These are the examples of ferromagnetic materials. So next, the magnetic field characteristics. Okay, magnetic field characteristics. So magnetic field in and around a bar magnet. Okay, in and around a bar magnet. Now the magnetic field surrounding a bar magnet can magnetograph. You can see on the right hand side. The magnetograph can be created by placing a piece of paper over a magnet. By placing a piece of paper over a magnet and sprinkling the paper with iron filling. Okay. Now what happens? The particles align themselves within the lines of magnetic force produced by the magnet, and it can be seen in the magnetograph that there are poles all along the length of the magnet, but that the poles are concentrated at the ends of the magnet. So there's the north pole and the south. Okay, they are having a piece of paper over a magnet, and some iron fillings are there on the sprinkled on the paper. Now the iron fillings are aligning themselves. Okay, and iron fillings or iron particles they are aligning themselves within the lines of magnetic force produced by the magnet, and which you can see on the magnetograph. And the you can see the poles also with that, the north pole and the south pole. Now the magnetic fields in and around the horseshoe or ring magnet. So these magnets they come in a variety of shapes, and one of the most common shape is the horseshoe magnet. Okay, horseshoe magnet. You can see in the diagram also how the horseshoe magnet is doing that. The lines are leaving the north and they are entering the south pole. Okay, and this is how you can say the flow of magnetic lines. The horseshoe magnet has south and north and south pole just like a bar magnet, but the magnet is curved. Okay, horseshoe magnet you can say the magnet is curved so that the poles lie in the same plane. Okay, now here the poles are in the same plane, so the horseshoe magnet is aligned in such a way that the magnet is curved and the poles lie in the same plane. So the magnetic lines of force flow from pole to pole. Okay, pole to pole, just like in a bar magnet. Okay, the flow of magnetic lines is the same, just like a bar magnet. However, since the poles are located closer together and a more direct path exists for the lines and a more direct path exists for the lines of flux to travel between the poles. So the magnetic field is concentrated between the poles. I repeat, you can see in the diagram also the poles are located closer together and more direct path exists for the lines of flux. Okay, so the magnetic field is concentrated between the poles. Now the general properties of we can say magnetic lines of force. Now see magnetic lines of force have a number of important properties like they seek the path of at least resistance between the opposite magnetic poles in a single bar magnet shown, and they attempt to form closed loops from pole to pole. They never cross one another. They all have the same strength, and their density decreases with an increasing distance from the pole. and their density decreases. They spread out when they move from an area of higher permeability to an area of lower permeability, and they are considered to have direction as it is flowing, as if flowing, though no actual movement occurs. And they flow from south pole to the north pole within the material, and north pole to the south pole in air. Okay, so these are some properties of MPF magnetic lines of force, and I think that we should start with the you can say uh, MCQs now, because uh, we should do with that. Okay, the MCQs for today. Uh, See, the MCQs are given to get you a slight idea of what you have studied. Okay, so try to answer the MCQs without seeing the answer. Just see the option and then try to answer the questions. It will help you to memorize the content that you have studied. Okay. Now it is a non-destructive testing. The first question, sorry, the first question. It is a non-destructive testing process for detecting surface and slightly subsurface discontinuities in ferromagnetic materials, such as iron, nickel, cobalt, and some of their alloys. I repeat, understand it. It is a non-destructive testing and NDET process for detecting surface and slightly subsurface discontinuities in ferromagnetic materials such as iron, nickel, cobalt, and some of their alloys. Now, out of all these things, the MPI, the magnetic particle inspection, is the right answer. Okay, because this technique is used to found discontinuities or defects or cracks in ferromagnetic materials. Okay, there is iron particles scattering over the crack, and the inspector can easily locate that crack easily. Okay, so the answer is magnetic particle inspection for that. Now, the second question is, which of the following defects are not detected by magnetic particle inspection? What kind of cracks are not detected by MPU? Okay, you can say. So, it is honest reflex. Now, you go with the magnetic particle inspection. Which of the following materials can be tested using MPI? So, out of these, if you think deeply, then you can say that the steel is the material which can be tested using magnetic particle inspection. Okay. Materials which have more iron in it, they are easily detected. They are easily inspected with the help of magnetic particle testing. Okay. Now, in magnetic particle inspection, what is the size range of how you should understand that how you can under what is the range of dry particle powder. See, these particle powder are helpful to you to accumulate near the crack. Okay, and where they form a cluster or where they assemble in a crack, you can easily find out that okay, here you can say the crack exists. So the size of this dry particle powder, the range of size is important. Okay, for us. So the range is from 5 micrometers to 170 micrometers. Okay. In this way, you can these are can be easily seen and easily located. So the size range of dry particle powder in MPI is 5 to 7 micrometers. Okay, sorry, 5 to 170 micrometers. Is 5 to 170 micrometers. The answer is A. 5 to 170 micrometers. Okay. Let's go to the next question. In an external, yeah, right, 170. In magnetic particle inspection, these magnetic particles have a large positive susceptibility to an external magnetic field. Okay, now they exhibit a strong attraction to magnetic fields and are able to retain the magnetic properties after the external field has been removed. Now, what do we call such particles, materials? Okay, now we have discussed this topic in detail also that the electrons the play very major role that if there are free electrons then you will get good magnetic fields. Okay, and also if you are able to retain the magnetic properties also when the external magnetic field has been removed. So when you talk about diamagnetic materials, is the correct answer or not? Diamagnetic material is not the answer. Ferromagnetic materials is the answer, or paramagnetic material is the answer. Paramagnetic materials is not the answer because this will not go. The answer is ferromagnetic materials. Ferromagnetic materials, they have a large external magnetic field. Okay, they have a strong attraction to magnetic fields, and they are able to retain their magnetic properties after the external field has been removed. So ferromagnetic materials, answer C is the answer. Okay, C is the answer. Option C is the answer. Ferromagnetic materials. Good. Now in magnetic particle inspection. Now these magnetic materials have a small positive susceptibility to magnetic fields. Now these materials are slightly attracted to by a magnetic field, and the material does not retain the magnetic properties when external field is removed. Okay. Now these have a slightly attracted to magnetic field. Okay, and they these materials have a small positive susceptibility to magnetic field. Ferromagnetic materials have large, okay, susceptibility to magnetic field, and also they retain their magnetic properties when the external field is removed. So C is not the answer. Ferromagnetic material is not the answer. Either diamagnetic material or paramagnetic material. So paramagnetic material are the materials which have a small positive susceptibility to magnetic fields, and paramagnetic materials are slightly attracted by a magnetic field, and the material does not retain their magnetic properties. Okay, the material does not retain their magnetic properties when the external field is removed. So the answer is B, paramagnetic material. Now in a magnetic particle inspection, any place that a magnetic line of force exists or enters the magnet is called a pole. We have two poles, North Pole and South Pole. Okay, so from one the magnetic line of force enters, and from one it exists. So it is called as a pole. The answer is true. Okay, and we have in this MPI we have two poles like a North Pole and South Pole, and they always occur in pairs. Okay, so in magnetic particle inspection, the only requirement from an inspectability standpoint is that the component being inspected must be made of a ferromagnetic material. That is a material that can be magnetized, such as iron, nickel, cobalt, or some of the alloys. Okay, you want that the only requirement that the you can say from inspectability point of view is that the ferromagnetic material, sorry, the component material must be made of ferromagnetic material. Okay, so that it is magnetized. Okay, so the answer is true, true in this case. Okay, true. And the options and the sorry the and the examples given as like iron, nickel, and cobalt. So the answer is true. Now, in magnetic particle inspection, it can be considered as a combination of two non-destructive testing methods like magnetic flux linkage testing and visual edge testing. So it is true. Now in magnetic particle inspection, these magnetic particles have a weak negative susceptibility to magnetic fields and are slightly repelled by a magnetic field, and the material does material does not retain the magnetic properties when external field is removed. So what do you call this? You call this as diamagnetic materials. Okay, you call this as diamagnetic materials. They have weak susceptibility to magnetic fields. Okay, and they also does not retain the magnetic properties when the external field is removed. These are called as diamagnetic materials. Option A. Diamagnetic materials. Option A. Now, these are the references which you can refer. And today we had a very nice discussion on a magnetic particle inspection technique of NDT, non-destructive evaluation and testing. This has its application more in case of ferromagnetic materials, and the advantages is that it is less costly and it is inexpensive and it is portable. So you can use this MPI technique when you have to find crack or discontinuities in case of ferromagnetic materials, and this will help the inspector also to have the clear vision with the help of cluster of iron particles on the crack and found the crack very easily. So these are the references which you can refer and increase your knowledge in this topic. This the context you can also try to read from these books, and it will give you a better understanding of the topic. So thank you all for now. Thank you.